Salam and welcome everyone. So today I am just compiling a bunch of shorter videos from my channel for any student who is reviewing your physical chemistry for an exam or for a test. The goal of this video is for you to review the examples that I've done already on this channel from the physical chemistry Atkins textbook. It is to help you in your journey through physical chemistry, whether you're about to take a test or whether you're doing a bunch of problem set. I wish you guys all the very best. Please enjoy the video. And so today we're going to be working on the question on the screen that says a sample of 6.56 gram of argon occupies 18.5 dm cubed at 305 kelvins. Calculate the work done when the gas expands isothermally. So the change in temperature equals zero. So basically what you're saying isothermally is that it's a constant temperature problem against a constant external pressure of 7.7 kilopascal until its volume has increased by 2.5 dnq. Of course, because an expansion, there's going to be an increase in volume. One thing you have to note when you're dealing with questions in physical chemistry is that you're either given one of the two. You're either given um a constant external pressure or a reversible reaction. And this is or a reversible process. And this only occurs when you're asked to find work done. So you can be asked to find the work done for a reversible process in an isothermal expansion, or you're going to be asked to find the work done when there is an isothermal expansion against a constant external pressure. Like in this case, we're given that. So you have two different formulas. So the formula for a question like this would be negative, okay, P external times change in volume. So this is all you need when you're solving a question that is an isothermal expansion against a constant external pressure. In this case, we know our pressure that we're given is 7.7 kilopascal or 7.7 times 10 raised to the power of 3 pascals, which is also the same thing as saying 7.7 times 10 raised to the power of 3 Newton per meter squared. Because basically, Newton per meter squared is the same thing as just Pascal. So that is the first thing you have to note. Now, looking at this question here, we see that work done, okay, is has its units in joules or Newton meter. So what I'm trying to explain to you here is that when you're given a question, before you can input the fact that you have the pressure or the change in volume, which is 2.5 dm cubed, you have to make sure that you have the units in the right form. You can see now we have the unit for pressure to be Newton per meter squared. But then we have the unit for change in volume. We have 2.5 dm cubed, by the way. We have the unit for volume to be in dm cubed, decimeter cubed. We cannot calculate a question when one is in a unit dm cubed and the other is in a unit of just meter. So what we have to do is we have to go from decimeter to meter. It's just like you being given a question where part of your question is in kilograms and the other part of the question is in grams. You need to change either from grams to kilograms or from kilograms to grams. Or sometimes you'll be forced to change from one unit to the other, and you can't just pick either of the two depending on the question. In this particular case, we'd have to go from decimeter cubed to meter cubed for volume. We cannot just use decimeter cube and input it in the equation. So what this is telling us is that we have to solve what 2.5 dm cube would be in meter cubed. So first of all, we have to remember the basic maths we did in elementary or middle school. You have 10 decimeter equals 1 meter. Hence, 10 decimeter cubed would be equal to how many meter cubed? I'm giving you this standard information because this is what you use. Just like 1,000 grams equals 1 kilograms, right? Hence, 10 decimeter is going to give you 1 meter. So yeah, that's just basically how it works. So in this case, we have to cube it in order for us to go from decimeter cube to meter cube. So you have 10 decimeter cube, the same thing as 1,000 decimeter cubed. And then 1 meter, all in brackets cubed, the same thing as 1 meter cubed. So now we're going from 2.5 decimeter to meter cube. So that would be using dimensional analysis. We have 2.5, okay, decimeter cubed times 1,000 decimeter cubed and then 1 meter cubed up top, of course. Yeah, and then 1 meter cube up top. So we cancel out the decimeter cubed and decimeter cubed, and what we end up with is 2.5 divided by 1,000. So that'll be 2.5 times 10 raised to the power of negative 3 meter cubed. And this is basically the answer for volume. So now we can be comfortable enough to input this information, because as you can see, the unit for pressure is Newton per meter squared, and the unit for volume is in meter cubed, because they are both in um some form of power of meter. We can use this information. So work done equals negative PEX, or negative external pressure times change in volume. So hence, work done is the same thing as negative. What is external pressure? That's 7.7 times 10 raised to the power of 3 Newton meter squared. So that would be 7.7 times 10 raised to the power of 3 Newton per meter squared. So that's it. And then we have the change in volume to be times 2.5 times 10 to the power of negative 3 meter cubed. Of course, because of we know how things work, we see that we've got meter square at the bottom, we've got meter cubed at the top, so we cancel the meter square and we cancel just the cubed, and we have just Newton times meter, which is what we would want anyways, because the unit for work is joules. So Newton meter equals joules, or joules equals Newton meter. So we're trying to basically see that our units are in the proper form, so we can continue safely to put this information in the calculator. So negative 7.7 times 10 to the power 3 times 2.5 times 10 to the power negative 3 would end up giving you negative 19.25 Newton meter. Now, if you look at our question, we would see that where the pressure as well as the change in volume is in 2 sig figs. So we have to put our information up until 2 sig figs. So hence, what work done actually is negative 19 Newton meter, or work done is equals negative 19 joules. So whatever you're using in terms of unit, you can use Newton meter or you can just use joules. So this is basically the answer to this question. If you're confused about what I did, what I just basically did in this question, because it's a very easy question, is for you to just write, for you to first of all determine that the formula we're supposed to use, and because it's an isothermal expansion at that is occurring against constant external pressure, this formula W equals negative P external times change in V is what you're going to use. The next thing we did is to put pressure under the unit, as well as change in volume, the unit for volume under the unit that is going to work for us. When we properly converted the units into the standard units that we can use for this calculation, we substituted the values, and then we just did unit cancellation, and we put information in our calculator, and we assigned the right units for work. That's basically what you do. Half of the work here is unit conversion, the other half is just knowing the formula, and then you get the right answer. If you have any questions, please put it in the comment section. If you would like to suggest any question or any topic to do, put it also in the comment section. Salam and welcome everyone. So today we're going to be working on the question on the screen that says a sample of 6.56 grams of argon occupies 18.5 dm cube at 305 kelvins. Calculate the work done when the gas expands isothermally in a reversible process, causing its volume to be increased by 2.5 dm cubed. So the first thing you have to do is, you're told that a sample of a particular amount of gas occupies 18.5 dm cube. Now, the first thing you notice, anytime in chemistry you're given the mass of something as well as the identity of that thing, what you're supposed to be looking for would be the number of moles. So just know you're going to be doing that in this question. And then you're telling you that occupies a particular volume. So this is V. And then at 305 Kelvin. So they have given us T. But then they say calculate the work done. So really what we're going to be looking for is work when the gas expands isothermally. So it's an expansion process. So we are going to have a V initial, which is this one right here. That basically what this one is in box. And then it said expands isothermally. So that is constant temperature. So constant temperature would also just mean like the change in temperature is zero. So during the entire process, the temperature is going to remain the same. So that's going to be this information right here. So in a reversible process. Now, this is the key to this question, because it's possible for you to be asked to find the work done when a gas expands isothermally, either in a reversible process or against constant external pressure. But because we're asked in a reversible process, the formula we're going to be used will be specific to this question, or to be specific to a reversible process. So that's going to be work done equals negative nRT ln V final divided by V initial. So we have the number of moles to be mass of argon, okay? So number of moles of argon equals to mass divided by molar mass of argon. So there's that. So yeah, that's it. So we have to determine that. We already know what the temperature is because we have that here. We have what the V initial is. We can determine the V final because it said causing its volume to be increased by 2.5 dm cubed. We can determine that as well. But let us first of all um write down all of the parameters before we start working with the work done equation. So we have number of moles of argon divided by mass. So that's going to be 6.56 grams divided by the molar mass of argon. And we know the molar mass of argon to be 39.948 gram per mole. So cancel out the grams, cancel out the grams. So the number of mole is going to actually equal 0.1642 mole. So that's basically what it is. And then you have the gas constant R, which is equal to 8.3145 joule per mole Kelvin. And you have the V final to be equal to change in V plus V initial. So V final is going to be change in V is 2.5 dm cubed because of course it's an expansion process, dm cubed plus the initial volume, which we have to be 18.5 dm cube. So the V final is going to be 21.0 dm cubed. So that's basically what the question is. Now, the last thing we have to do now is, since we have the number of moles, the V final, the V initial, the temperature, the gas constant, we can just substitute. And that's basically how you solve a question like this. So W equals negative 0.1642. So that's mole, okay, times R, which is 8.3145 joule per mole Kelvin, times temperature, which is 305 Kelvin, ln V final divided by V initial. So that would be 21.0 dm cubed divided by the V initial, which is 18.5 dm cubed. So dm cube cancel out. So you have next W equals negative. We're going to cancel out all the units that we're not using because normally the unit for work is joules. So we want to make sure everything is in joules. So cancel out moles, kelvins. Kelvin. And now we just have negative 0.164 times 8.3145 joules times 305. We're going to get that to be negative 416.4327 joules times natural logarithm of 21.0 divided by 18.5. So that's basically it. So work done now is going to be equal to negative 52.7853 joules. So that's going to be work done equals negative. So you have three sig figs for the mass. You have 360 for the initial volume, have 360 for temperature, and the final volume, when you add it to the initial volume, you end up with 21.0. That's also three sig figs. So this question is saying that we have to do it because that's how you do it in chemistry. Your calculation, you have to round it up or around it. You're just going to have to approximate to the sig figs that you're supposed to be using, right? So we are supposed to be using three sig figs here. So that's going to be 52.8, sorry, negative 52.8 joules. So this is basically the work for this question, the work done for this question. So you guys can see it's very easy peasy. So it just requires you to know the knowledge and for you to do everything step by step. I wish you guys all the very best. Salam and welcome everyone. So today we're going to be working on the question on the screen that says a sample of 4.5 grams of methane occupies 12.7 decimeter cubed at 310 degrees Kelvin. Calculate the work done when the gas expands isothermally against a constant external pressure of 200 torr until its volume has increased by 3.3 dm cubed. So from this question, we know that we're supposed to solve for work done when isothermal expansion occurs. So here the change in temperature is zero, meaning the temperature for this entire process will be 310 kelvins. And this occurs against a constant external pressure of 200 torr. So one thing you have to know is when you look at the first part of the question, when they tell you that there's an isothermal expansion, you could have a situation where it is an isothermal expansion that is reversible or that is against constant external pressure. And whichever one that you're given is going to actually determine the formula that you would use. Because this question is against a constant external pressure, we're going to use W equals negative P external times change in volume. So what we're really going to be focusing on in the parameters that we're given here would just be the fact that pressure is 200 torr and change in volume is 3.3 dm cubed. So we're going to just input all of that information inside this. But the issue with this is that because the unit for work is in joules, which is we can also say that to be Newton meter, none of the information here is giving us none of the information that we have here is showing us is showing us that we could get joules from this. Generally, the SI unit for pressure is like the unit that would work for a question like this for pressure is in pascals, and the unit that would work for change in volume in a question that involves joules is meter cubed. So volume will like it in meter cubed. So we have to go from dm cubed to meter cubed. And then torr, we have to go from torr to pascals because pascals is also Newton per meter squared. So you can see now Newton per meter squared and meter cubed, they at least have something in common where meter is a unit in both of them so that we can do our calculation properly. So what I'm trying to tell you is that we don't have our question, our pressure, and our change in volume in units that would work for this type of question. So what we have to do now, before we can even input or use the formula, is for us to solve for all of this information in the proper units, then we can successfully substitute. So the first thing you do is you should not forget that pressure, okay, here is in torr. So if we're trying to go from torr to pascals, we have to remember that 1 atm, this is what I actually used to remember all the time, 101,325 pascal. So one atmospheric pressure is the same thing as 101,325 pascal. And then one atmosphere is actually 760 torr. Hence, looking at this information, we know that 760 torr, so this is a standard conversion, is going to give you 101,325 pascal or Newton per meter squared, which is what we're trying to go. So this is a standard one. But in our question, we're given 200 torr. So we're supposed to now find what would 200 torr give you based on this fact that I am boxing right here. What is 200 torr going to give you? So of course we do dimensional analysis to solve this. So if we're given 200 torr, okay, and we know that the standard is, we're going to put the torr at the bottom because we're doing unit conversion or dimension analysis. We're doing unit conversion using dimension analysis. So we're not going to put 760 at the denominator and then 101,325 Newton per meter squared, or you can just call it pascals. So torr cancel torr, 200 divided by 760 times 101,325 Newton per meter squared. All of that information is supposed to give you 26,664.474 Newton per meter squared. So this is basically what you're gonna have. Now we've been able to successfully determine what the pressure is. Now we're supposed to determine what the volume will be from dm cubed to meter cubed. So note this, and I'm going to teach you this. And if you've been watching my videos, you know that I always do this. We're going from dm cubed to meter cubed. And some of you may be confused that how do you do this? Well, one way you can do this when you're doing unit conversions like this is for you to just remember that 10 decimeter actually just gives you 1 meter, and 10, that's just the fundamental, right? Just like 1 kilograms is the same thing as 1,000 grams. So we know that 1 meter is equivalent to 10 decimeter. So in order for you to go from just decimeter to decimeter cube and for you to go from meter to meter cubed, you just have to cube the standard information that we know. So we're going to cube this. So we know 10 times 10 times 10 will give us 1000. Dm cubed, sorry, dm times dm will give you dm cubed. And 1 times 1 will give you 1. Meter times meter times meter will give you meter cubed. So we go. So this is the standard information. But then we're told that the change in volume we're dealing with is 3.3 dm cube up top, the one I'm putting in the purple box. So what we just do is 3.3 using dimension analysis again, dm cubed times 1000 dm cubed, and then 1 meter cubed up top. So you cancel out dm cubed. Sorry, you cancel out dm cubed and cancel out dm cubed. 3.3 divided by 1000 would just be 3.3 times 10 raised to the power of negative 3 meter cubed. And this is basically what you have to be the answer. So, yeah, that is it. That is basically the answer so far. But that's not the answer to our actual question because we're actually supposed to be solving for work done. So now we have all the units in the proper parameters. So we just say work done. So we're just going to rewrite the information. So work done equals negative P external times change in V. So work done is going to be negative P external is the same thing as saying yeah, it's same thing as 26,664.474. So that would be negative 26 point, sorry, negative 26 comma 664.474 Newton per meter squared. Again, the pressure can also, pressure is basically force divided by area. So the unit for force is Newton, the unit for area is meter squared. So we're using the SI unit here in order for us to be able to properly solve for joules. Okay, times change in volume, we just did that. That would be 3.3 times 10 raised to the power of negative 3 meter cubed. So of course we cancel out meter squared, cancel out this. So you've just got Newton here, you've got meter. And what is joules again? Joules is the same thing as Newton meter. So I just wanted to put that there. So when you put this information in the calculator, 26,664.474 times 3.3 times 10 raised to the power negative 3, what you're supposed to get is negative 87.9928 Newton meter. Or we have to remember that since this is a chemistry problem or a science problem, we always have to remember to use sig figs. So in this case, everything that I'm seeing right now, at least that we're using in this question, we've got 200 torr. We have that in 3 sig figs. We've got 3.3 dmq. We have that in 2 sig figs. So 2 sig figs is less than 3 sig figs. So we're supposed to use the lesser significant figures in chemistry or in science. So we're supposed to round up until 2 sig figs. So that would be negative 88 Newton meter, or you can just say W equals negative 88 joules. And this is basically the answer to the question. You can see half of the work is mainly unit conversions. So you really need to know unit conversions in physical chemistry or thermodynamics. And when you know the unit conversions for a question like this, half of the work is done. You just have to use basic math. If you have any questions, make sure you put it in the comment section. If you have any suggestions, put it in the comment sections as well. Salam and welcome everyone. So today we're going to be working on this question on the screen that says a sample consisting of 1.0 mole of argon is expanded isothermally. So this question is telling us that the final volume is going to be greater than the initial volume. So since that's an expansion, and then we have that it's isothermal in nature. So that means the change in temperature is 0, which just simply means that this process or reaction occurs at constant temperature. And then they tell us the temperature is 20 degrees Celsius from 10.0 dm cube to 30.0 dm cube. Calculate the work done when the process occurs reversibly. So this is just basically the question. First, we're going to write down the parameters. We know the number of moles is 1.00 mole. Okay. We know that the temperature is 20 degrees Celsius. But because this is a physical chemistry question, we know that we like the temperature written in Kelvin. So that's going to be temperature equals 20 plus 273.15. So temperature equals 293.15 Kelvin. And then we have volume, V initial to be 10.0 dm cubed. And then V final to be 30.0 dm cubed. Okay, so We have all of this information. We are now supposed to calculate the work done when the process occurs reversibly. So, right, the work done, W equals negative nRT ln V final divided by V initial, right? So, yeah, now our job is to basically input. So one thing I wanted you guys to know is that all the work done formula would be different depending on what you're doing. This question is an isothermal expansion that occurs reversibly. So basically our question is going to have this formula. If, for example, this was not an if this was a question where it's against constant external pressure, the formula we're going to use to calculate work done is going to also be different. So be very careful because this is an exothermal expansion and it occurs reversibly. That's the reason why we're using this particular equation. You can be given a completely different question where they say instead of reversibly, they say against external pressure or against constant external pressure, and you're going to be using a totally different formula. So if you want to know how to solve a question like that, make sure you check the description box and watch that video. So work done equals basically all this information. So the next thing you have now is just for you to input. So work equals negative and then 1.0 mole, okay, times the gas constant that we're going to be using in this equation. Because of we know work and what is work, work unit is in joules. We're going to be looking for a gas constant that we can impute inside this particular equation where we can be able to get our answer for work in joules. So the our gas constant we're going to be using is going to be 8.3145, okay, joules per mole Kelvin. So this is one of the gas constants with the units joules per mole Kelvin. So that's going to be inputted here. So that'll be 8.3145, okay, joules per mole Kelvin times temperature will be 293.15 Kelvin, and then ln V final divided by V initial. So that'll be 30.0 dm cubed divided by 10.0 dm cubed. So you cancel out the dm cubed, cancel out 10, 10, that would be 3 over here. So Kelvin, Kelvin, mole, mole. So work is now going to be W equals negative 8.3145 times 293.15 times 1 is going to give us the answer negative 2437, okay, 0.396, and then of course ln 3. And when we do that, oof, my pen is not doing right. Please don't do this to me right now. Okay, so yeah, ln 3. Sorry, let me just erase this not scribbled nonsense. So that would be ln 3. So yeah, this work done now is going to be negative blah 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 ln 3. So that will be times ln 3. So when you put down your calculator, you're going to get negative 2677.8. And of course, let's not forget the unit joules. Joules. So yeah, but then we have to go back to our question, right? Our question that we're given, we see that 1.0 is 3 sig figs, 10.0 and 30.0 are all 3 sig figs. So we're supposed to put this our answer in 3 sig figs. So that means our numerical value, sorry, our numerical information is supposed to stop at 7. So we end up with work done equals negative 2.68 times 10 raised to the power of 3. So using the scientific notation to make sure we keep it in 3 sig figs joules. And this is the answer. Before we go on, I wanted to explain the reason why we have a negative here. We have a negative work done because in thermodynamics or in physical chemistry, we're dealing with the system, how a system or how a machine or how a reaction or how a container filled with reactant, of course, a system is whatever we're studying, and then the surrounding is everything outside whatever we're studying. So when you understand that, you know that we're looking from the perspective of the machine. Now, the reason why the work is negative is because during the isothermal expansion process, energy is being used for the expansion process, right? And if energy is being used for something, it's going to have less energy. It's just like, say, I want to clean my room. The energy I have at the beginning of cleaning my room is going to be greater than the energy that I have than the energy I have after I clean my room. So this negative here is denoting the fact that there is lesser energy after you are done with a particular task. So after the system undergoes the expansion, there is lesser energy. So if you have any questions, please email me at shuhabitutoring@gmail.com. I wish you guys all the very best. Salam and welcome, everyone. So today we're going to be working on the question on the screen that says a chemical reaction takes place in a container fitted with a piston of cross-sectional area 50 centimeters squared. So we have the area of the piston to be 50 centimeters squared. As a result of the reaction, the piston is pushed out through 15 centimeter against an external pressure of 1 atm. So basically, the distance that the piston traveled is 15 centimeter, um, just basically the distance as a result of the reaction. And that is done against external pressure, so P external of 1.0 atm. So we're supposed to calculate the work done by the system. So a question like this is not easy because it's very tricky. You have to first of all draw out the information to see how like it can work. So you have this piston. So we're going to draw a before and after the reaction occurred. So you have this piston, then you've got a reaction. So, sorry, not this is not a piston, this is a container. So this is the piston that I'm currently drawing in the middle of the container. So there is an external pressure that is acting upon it, and this external pressure is called 1.0 atmosphere, right? And we know that it has cross-sectional area, which is the piston I'm talking about. And basically the area of this is just the area of the piston is 50.0 centimeter squared. Now the reaction occurred, and now the piston traveled and it went up. We still have the external pressure that is acting on it, which is simply 1 atm. So that is still there. So 1 atm is the external pressure. Now let us calculate whatever is going on here. You've had this here, and if you trace this, you have this. So this situation here is what is showing you that the piston is pushed through 15 centimeter. So what this is saying, the distance traveled by the piston as work is being done by the system is just 15 centimeter. So now we're asked to solve for the work done by the system. So this is basically it. We've been given the area, we've been given the distance traveled during the expansion process. We've also been given the value of external pressure, which is 1 atm. So the first thing you have to do is, let's not forget that work is equals to force times distance. And we don't have the value for force, but we have a value for distance. But before we go ahead, we remember now that since we're dealing with work done by the system, we can't just say work equals force times distance. Actually, work is now equals to negative force times distance. So now work here equals negative force times distance. So that is it. Now, to remember what is going on here, we don't have value for force, we have value for distance. So we have to be able to find what we're looking for based on what we're given. We have to remember that fundamentally, pressure that we're given is the same thing as force divided by area. So if the pressure, so let me now give you like an example of how this works. When you want to calculate the pressure of something, you have to, first of all, divide the force by the area, right? Now we know that pressure is equals to force times area. What we can just simply do is for us to cross multiply, right? To determine this, what the value for force is. The force now is going to be equals to pressure times area. So work done is equal to negative pressure times area times distance. And this is basically what we're going to use to solve this question. So we have work equals negative pressure times area times distance. We have all the units that we have all the parameter information we need. We have the pressure, we've got the area, we've got the distance. Now, let's not forget that we can just solve for area and distance. So I'm going to rewrite this equation as negative pressure times area times distance, which is the same thing as volume. But the issue we have here now is this. We're given the area, which is 50 centimeters squared, as well as the distance, which is 15 centimeter. We're given both of them in centimeter. So hence, in order for us to properly work with this question, we have to go from centimeter to meter. And part of the reason why this is the case is, let's not forget that force is equal to, sorry, let's not forget that pressure is equal to force times distance. The unit for force is Newton. The unit for area is meter squared. We cannot have a situation where we're working with centimeter and meter in the same question, because for example, now we're going to be dealing with centimeter squared as well as just meter. We cannot cancel out the units that way. Hence, we cannot get the proper calculation, because we need to make sure everything is converted into the standard unit so it's easy for us to solve the problem. So we have AD, which I can just simply say AD, or A times is the same thing as 50 centimeter squared times 15 centimeter. So that's going to be centimeter cubed. So 150 times 5 is just a way for me to say 50 times 15. That's when you solve it and put in your calculator, you're going to end up seeing that is the same thing as 750 centimeter cubed. So we go now from centimeter cube to meter, to whatever meter cube is, right? So let's not forget that 1 meter is actually equal to 100 centimeter. So now if we're trying to go from um centimeter cubed to meter cubed, we now have to do this thing where we're going to cube the standard information here. So we're going to say 1 meter all cubed equals 100 centimeter all cubed. So that's going to be equivalent to 1 meter. Sorry, that's going to be equivalent to 1 meter cubed equals 100 times 100 times 100. That would be 1,000,000. And then centimeter times centimeter times centimeter, that's going to be centimeter cubed. So we're now going to have to go from 750 centimeter cubed to whatever this is. Now we've gotten the standard information that we need to do this conversion. So we're now going to have 750 centimeter cubed times 1 meter cubed, because it has to be at the numerator since that's what we're solving for, to 1,000,000 centimeter cubed. So we do our math, put this in a calculator, and while we're doing that, we can just cross out the units. When we do the whole thing here, we end up with 7.5 times 10 raised to the power of -4 meter cubed. Yep, that is it. So now we can use this information in the pressure that we're given. So let's not forget W equals negative P times AD. So negative external pressure. So that would be W work done equals negative P external is just simply 1.0 atmospheres. I can use my brain and go from 1 atmosphere to Pascal, right? Remember Pascal, the unit for Pascal is just simply Newton per meter squared. So since we're given the pressure in 1 atmosphere, remember that 1 atmosphere is the same thing as 101,325 Pascal, or 101,325 Newton per meter squared. So this is it. So now we're going to just input this one. That will be negative 101,325 Newton per meter squared times what we've got in here, which is the area times distance. So the volume, that will be times 7.5 times 10 raised to the power of -4, and then of course meter cubed. Let me separate this so it doesn't mess up our work. So work done equals meter here, meter square here, and cancel meter. That will be -101,325 Newton times -7.5 this. So basically what we end up with -75.9938, okay, Newton meter. So work done is going to be -76 Newton meter, or we can just say work done is going to be -76 joules. So that is basically the answer to this question. So if you have any questions, please leave it in the comment section. I wish you guys all the very best. Make sure you keep working hard and keep striving to succeed. Salam and welcome. So today we're going to be working on the question on the screen that says a chemical reaction takes place in a container fitted with a piston of cross-sectional area 75.0 centimeter cube. So we have the area to be 75.0 centimeter squared. Sorry, not centimeter cube, centimeter squared. As a result of this reaction, the piston is pushed out through 25.0 centimeter against external pressure of 150 kilopascal. So we have a distance traveled by the piston as a result of the reaction to be 25.0 centimeter. And this happens against an external pressure. So P external, which is 150 kilopascal. And we're asked to find the work done by the system. Now, the first thing you have to do in a question like this is for you to basically draw so that you can see like the reality of what you're working with. So the first thing you do is you're going to draw the piston before the reaction. Sorry, you're going to draw the co- um container before and after the reaction and everything that is going on in it. So the piston is what I'm drawing right now. You see that the piston is this, and we're told that it is 75.0 centimeter squared. So area is 75.0 centimeter squared, and we have the distance traveled by the piston, and that is going to be 25 centimeter. So that's the distance. Now, if we look at our work from here up until here, this is the distance traveled. So this whole thing here is 25 centimeter. So that's how much is traveled when work is doing the distance. So from the beginning, before work started on the system and after work started. So it is a 25 centimeter distance that piston traveled as a result of the work done by the system. Now, the external pressure that was being applied is 150 kilopascal. So that's what the pressure is. So that's basically it's 150 kilopascal. So we're being asked now the work done by the system. So when we go back to the fundamental explanation or definition for work, we know work is force times distance. That is basically what work is. But because it's a situation where work isn't being done by the system, the work is going to have a negative value because the system is doing work. Hence, the negative value shows that work is being lost. Energy is being lost by the system because the system is doing work. So we're going to denote it as a negative. And then we have force times distance. Now you can see that from our information, we're never given the value for force. We're only given the value for area and the value of distance. But when we think of our fundamental understanding of chemistry, we know that pressure that we're given is the same thing as force divided by area. Hence, when we solve this equation in a box in terms of force, we end up with force equals pressure times area. Now we have what we need. So we're going to input it in the equation here. Work, which is negative force times distance, is now going to be negative pressure times area times distance equals basically work. So this is it right here. So that would be work equals negative pressure, blah, 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 blah. Negative pressure times area times distance. But one thing you have to know is that I'm going to be rewriting this negative pressure times area times distance. I'm putting area and distance in the bracket just because they have similar units, and you're going to see the reason why I'm doing it in a second. So we have the value for area to be 75. We have the value for the distance to be 25. So area, just looking at this one here, area times distance, 75 centimeter squared times 25 centimeter would give you 1,875 centimeter cubed. This is basically the answer to the question. So, yeah, work now is going to be negative pressure, external pressure, times AD. So that would be times AD. Now, the normal thing we're supposed to do, it would have been for us to basically just multiply everything. But we have to remember that pressure, right? Oh gosh, what's going on with this pen? So now the normal thing we're supposed to do would just be to just input the information in the equation here. But this cannot happen because even though we have the value for pressure and then area and then distance, the issue we have with this question is that we know that pressure is force over area. Okay, so hence the unit is Newton per meter squared. In this case, we have kilopascal. Um, that's just basically times 10 to the power 3 Pascal. Well, the unit for Pascal is also Newton per meter squared. But then we have the volume in terms of centimeter cubed. Hence, we cannot put centimeter and meter in the same calculation because we need the units to be similar in value, and basically the degree that is on top of the unit, we need it to be similar in order for us to do any further calculation. So what I'm trying to tell you is that we have to convert centimeter cubed right here to meter cubed. That's just it. We just need to do unit conversion. So we know generally, because we learned it in elementary school, we know that 100 centimeter equals 1 meter. Hence, 100 centimeter all cubed is going to give us 1 meter all cubed. So doing the math would just mean 100 times 100 times 100. That's going to be 1 million centimeter cubed equals 1 meter cubed. So that is it. So we're going to use this information that we have to solve. We're going to use this information that we have to solve and get the value of 1875 centimeter cube in meter cubed. That's just basically what I'm trying to say. So we're going to say 18. Let me separate. We're going to say 1875 centimeter cubed times, using dimensional analysis, 1 meter cubed would be up top because we're trying to solve the question in in meter cubed. And then you have the 1 million centimeter cubed. So we cancel out centimeter cubed, cancel centimeter cubed. 1875 is the same thing as us getting 1.875 times 10 raised to the power of negative 3 meter cubed. And this is what we're going to insert in our question. So now we have this 1875 centimeter cubed in meter cubed. Now we have the pressure. What is the pressure again? The pressure is 150 kilopascal. Well, remember now that 150 kilopascal to Pascal is the same thing as saying 150 times 10 to the power 3 Pascal, or 150 times 10 to the power 3 Newton per meter squared, because Pascal is the same thing as Newton per meter squared. And we're just going to input all of that information in our equation on the left. So let me use a different marker. So W equals negative, the P external is 150 times 10 raised to the power 3 Newton per meter squared times the value for volume. So that would be 1.875 times 10 raised to the power negative 3 meter cubed. So cancel out meter squared, remove cubed from meter. So work done equals negative 150 times 10 raised to the power 3 times 1.875 times 10 raised to the power negative 3. So just cancel out this side and this side, basically the negative 3 and the positive 3. So when you do the calculation in your calculator, you end up with 281.25 Newton meter. And since, of course, this question that we're given is in 3 sig figs, we can stop writing the value on that one. So that's going to just be W work done equals negative 281 Newton meter, or work done equals negative 281 joules. Don't forget, Newton meter is the same thing as joules. just like pascals is the same thing as Newton per meter squared. And this is basically how you answer a question like this. If you have any questions, please put it in the comment section. Salam and welcome everyone. So today we're going to be working on the question on the screen that says a sample consisting of 1.00 mole of argon is expanded isothermally. So in this case, we've seen that we have an isothermal expansion problem where there is going to be an increase in volume. So V final is going to be greater than V initial, and the process is going to be occurring at constant temperature, okay, at 20 degrees Celsius from 10.0 dm cube to 30.0 dm cube. Calculate the work done when the process occurs against constant external pressure that is equal to the final pressure of the gas. So one thing you have to know is that whenever you're given a constant external pressure question and you're told to calculate work, what this means is that work equals negative P, as in the external pressure, right? Times change in volume. So the first thing you have to do is that you have to be able to find what pressure is, and we have, of course, what the change in volume is. Ignore the other parameters, which is the number of mole. Also ignore the fact that the temperature is given. Also ignore the fact that the volume is given in dm cube. Right now, let's just talk about pressure. Well, the question says against constant external pressure that is equal to the final pressure of the gas. If you've noticed, they did not give us what the external pressure value is. They just told us that P external is the same thing as P final. So the final pressure and the external pressure are going to be the same thing. Now, since this is a question where we're assuming that this is perfect gas, we're going to use the very important formula, which is PV equals nRT, right? And in this case, we're going to be solving for P final. So P final equals nRT, okay? And then this V, we're going to put this equation in terms of P final. So that's going to be divided by V final. So we're going to be using the final volume because we're looking for the final pressure. So if we're looking for the initial pressure, we'll be using the initial volume. So this is the reason why I'm having V final here and I'm not picking any other volume. So we have this now. We do the math. We use the number of moles that we're given, okay? Now we can use the number of moles, the gas constant, and the temperature. Number of moles we're given is 1.00 mole, okay, times 8.3145, okay, and that's going to be kilopascal, okay, dm cubed divided by mole Kelvin times the temperature, which is given to us. And the temperature here is 20 degrees. So 20 degrees to Kelvin is the same thing as saying 20 plus 273.15. So the temperature is actually 293.15. Sorry, 0.15 Kelvin. So we're going to have that here. So that would be 293.15 Kelvin. All of this information is divided by the final volume. So that would be 30.0 dm cubed. So we're going to cancel out dm cubed, dm cubed, Kelvin, Kelvin, mole, mole. So we're going to cancel all of this information out. And we would end up having P final equals 1 times 8.3145 kilopascal times 293.15. Divided by 30. So whatever this answer is going to be the answer for the P final that we're going to need to solve for the work. So yeah, this is just part of the process. So when we do that, we have 81.2465 kilopascal. So this is basically what this is. So this is actually the pressure. Now, don't forget that this kilopascal can be rewritten as 81.2465 times 10 raised to the power of 3. Yeah, Pascal. So that's basically what kilopascal is. So now this question is now asking us for the work done. So that would be W equals negative P final change in volume. But one thing you have to note is this. Pascal, right, is the unit for pressure. What is pressure? Pressure is simply force over area. So that is what pressure is. That's like the fundamental definition of pressure, force over area. Well, the units for force is Newton. So this is just make sure you remember your physics that you've done in college and in high school. Area, the standard unit or the SI unit for area is meters squared. SI unit for force is Newton. So really, Pascal is the same thing as Pascal. Sorry, is the same thing as Newton per meter squared. That's like another way to denote Pascal. So that would be Newton per meter squared. So I wanted to put that information down first because we're going to be using that. But then let's also not forget what volume is, right? We're asked to find the change in volume. Well, we know what the change in volume is, right? The change in volume here is just going to be V final minus V initial. So that would be 30 point 0 dm cubed minus 10.0 dm cubed. So change in volume is going to be 20.0 dm cubed. So yeah, that's basically what you do. Now we see that dm cubed and we see meter. So we have a dm here, decimeter, and we have a meter here. And honestly, they cannot cancel out. They would need either the decimeter should be converted to meter or the meter to be converted to the decimeter. But the wise thing is for us to change from decimeter to meter. So that's going to be decimeter to meter. Well, let's not forget 10 decimeter, okay, is actually going to give you 1 meter. So hence 10 decimeter cubed, right, is going to give you what? Right? Sorry. So hence decimeter cube will give you how many meter cubed? Well, if we cubed both the right and the left of this particular equation, we're going to note, we're going to see that 10 times 10 times 10 is simply 1,000, and 10 times 10 times 1,000, dm times dm times dn is dm cubed. 1 times 1 times 1 is 1, meter times meter times meter is meter cubed. So that means for every 1 meter cube, you're going to have 1,000 decimeter cubed. So basically what I'm trying to do here is to go from decimeter cubed to meter cubed. So I'll use a black pen now. So yeah, so let's not now forget that if that's the case, we've seen that the change in volume is 20.0 decimeter cubed. So we're going to do dimensional analysis and say 20.0 decimeter cubed times, we're going to have 1,000 decimeter cubed right here because we're trying to find it in meter cube, divided by 1 meter cubed. Well, since we're not dealing with decimeter, we don't want it in decimeter, we can cancel out decimeter, and then will be 20 divided by 1,000. So that's 20 times 10 to the power negative 3, which is the same thing as the change in volume in terms of meter cubed is going to be 0.020 meter cubed. So this is what we're actually going to input in this particular equation. So hence, work done here that we know it to be negative P final, change in V is the same thing as, so work done, negative P final, change in V. So that will be work done equals negative 81, 81.2465 times 10 to the power 3 Newton per meter squared. Okay, don't forget that's what Pascal is, times change in volume, which is 0.020 meter cubed. So of course we're going to do the math we know how to do best. Meter squared, remove the cubed. So that's going to be W work done is going to be negative 81.2465 times 10 to the power 3, okay, times 0.020 Newton meter, which is the same thing. Just remember that Newton meter is joules, same thing as joules, right? Just like Pascal is the same thing as Newton per meter square. So now we input this information to the calculator and we get negative, done equals negative 1624.93 Newton meter. So in 3 sig figs, we're going to get, because basically that's what our question is, right? We're given in 10.03 sig figs, 1.003 sig figs, 30.003 sig figs. So everything is in 3 sig figs. So work done is just going to be negative 1.62, okay, times 10 to the power of 3, since it's sig figs, Newton meter, or work done is negative 1.62 times 10 to the power of 3 joules. And I also wanted to quickly mention that the reason why our work is a negative is because the work is being done by the system. Whenever a system is doing work, like in this case, an expansion is going where there is like an increase in volume, the system is actually doing work. After the process has occurred, the expansion process has occurred, the system now has lesser energy. It's just like if I clean my room, after I'm done cleaning my room, I'm going to have lesser energy. So the negative in front of the numerical value is showing you how much energy has been lost through the whole isothermal expansion process. I wish you guys all the very best. If you have any questions, please put it in the comment section. Salam and welcome everyone to my channel. So today we're going to be working on the question on the screen that says a sample consisting of 2.0 mole is expanded isothermally. So expansion is just saying the final volume is greater than the initial volume, or there has been an increase in volume during the reaction or the chemical process. So it's expanded isothermally at 0 degrees Celsius. So isothermally is telling us that we have a constant temperature process, and that constant temperature, the temperature that is constant through the entire process, is 0 degrees Celsius from 5.0 dm cubed to 20.0 dm cubed, hence why it's an expansion or an increase in volume. So now we're supposed to calculate the work done by the system when the process occurs reversibly. So the first thing we have to do is to write down parameters. So we have the parameters n equals 2.00 mole, okay? We have the temperature equals 0 degrees Celsius, which we can convert to Kelvin. So we have 273.15 plus 0 is the same thing as 273.15. And because now it's in Kelvin, we're going to put the K there. And we have the initial volume, V initial, to be 5.0 dm cubed, V final to be 20.0 dm cubed. So calculate the work done by the system when the process occurs reversibly. So yeah, well, W stands for work, and you have negative nRT ln V final divided by V initial. This is what we're going to use. The reason why we use this particular equation is because this is an isothermal expansion process that occurs reversibly. It is possible for you to have an isothermal expansion problem that occurs against constant external pressure, and that one has a totally different formula from this one that I just wrote down. That one has a complete different formula, a complete different technique in solving to get the work done. So just note that when you are asked to solve questions, note whether they're asking you for a reversible process or they're asking you for against zero or free expansion, or thirdly, if they're asking you against constant external pressure, because they can ask you any of the three. So that's very important for you to know. So now we have this information. All we have to do is just simply substitute. So we have work equals negative 2.0 mole times 8.3145 joule per mole Kelvin times temperature, which is 273.15 Kelvin, ln V final divided by V initial. So that will be 20.0 dm cubed divided by 5.0 dm cubed. So we're going to cancel out all the information. So we're going to cancel out the moles. Sorry, not all the information, all the units. We're going to cancel out all the Kelvin. We're going to cancel out the dm cubed. And what we have left is joules. Now, I wanted to mention that the reason why we're using this gas constant, which is R equals 8.3145 joule per mole Kelvin, is because when you look at the gas constant list, you're going to find different units. But because this is a question that involves work, we're going to use the units where the numerator is joules, or is in form of the unit for work, which is joules. So basically, this is what's going on here. That's why we're not using any other one, but we're using this particular one because this is what works best for this question. So hence, we have work equals negative 2.00 times 8.3145 times 273. Okay, whatever that is, you input that in your calculator, you end up getting negative 4542.211 joules, and then ln 5 divided 5 in 5 1 5 in 24, so that's going to be ln 4. So now you would now say this whole information you just calculated times the logarithm of 4. So when you input that in your calculator, you're going to end up with negative 6296.842 joules. Or you're going to go back to your question. Basically, this is correct, but let's not forget that because the chemistry work problem, you have to be very careful how you handle like significant figures and decimal places. So you can see that we have three sig figs for the number of moles. We've got two sig figs for one of the volume and three sig figs for the second one. We're going to stick to the two sig figs for the second one because we're going to pick, because that's how it is in maths, right? You're going to take the sig figs of whatever is the lowest sig figs in the values of the question that you're given. So which is two sig figs. So it's going to be two here. So that means the work is going to be negative 6 point approximately. So you end up with negative 6.3 times 10 raised to the power of 3 joules. So this is the answer to the question. Now, quickly, I'm going to mention that the negative sign here is just to tell you that since work is being done by the system is going to have lesser energy before the process occurred in comparison to after expansion occurred. Because of expansion was done by the system, right? Meaning actual work was done by the system, there's going to be a lower energy after the entire expansion process. So the energy lost as a result of the expansion process is 6.3 times 10 to the power 3. And because it's lost, we denote it with a negative. So basically, this is the answer to this question. Make sure you watch more videos for practice. I wish you guys all the very best. If you have any question, put it in the comment section. If you Salam and welcome everyone. So today we're going to be working on the question on the screen that says a sample of 4.50 grams of methane occupies 12.7 dm cube at 310 kelvins. So first of all, you're given the mass of gas, and that gas is methane. So we've been given the identity and the quantity of the gas. Whenever you're given the mass as well as the identity of a gas, just know that indirectly they're trying to tell you that you have to solve for a number of moles. So that's always what ends up happening in chemistry. So put that in mind. And then you're told that it occupies 12.7 dm cubed. 12.7 dm cubed is the same thing as the volume at 310 Kelvin. So this is the temperature. Calculate the work done. Okay, so we're asked to calculate work when the gas expands isothermally. Okay, in a reversible process. So this is good because this is the key information we need to solve this, because it's possible for a gas to expand isothermally when we're dealing with whenever we're dealing with a question that asks us to solve against constant external pressure. But because they said this is a reversible process, they've made our work easy because now we can just write down what the formula is. So for to determine work that occurs in a reversible process when the gas expands isothermally, we have W equals negative nRT ln, so lateral log the V final divided by the V initial. So that is what it is. So in a reversible process, causing its volume to be increased by, so not increased to, of course, it's not increased to because this is going to be less than increased by. So whatever the initial um, volume is, which we're told here is 12.7 dm cubed, the final volume was just going to be this, whatever the initial volume is plus the change in volume. So hence V final here, which we don't know, is just going to be the V initial plus the change in volume. So the V final is just going to be 12.7 dm cubed plus 3.3 dm cubed. So the V final is just going to be 12.7 plus 3.3 is the same thing as 16.0 dm cubed. So that's how you work with this one. So we know what the V final is. Now we have to determine the number of moles because we actually know what the gas constant is. Anytime you're dealing with a work problem, remember that the unit for work is either Newton meter or joules. So one of the two, Newton meter or joules. So you have to pick the gas constant that actually matches the units that we are trying to solve for in the question. So looking at this, we have to look for a gas constant. We have to use the gas constant that has the unit of joules or Newton meter, and we have our R to actually be 8.3145 joules per mole Kelvin. So all this information is necessary because we ultimately want to write down all the information that we're given. So when we put all of this information and we substitute to find work, we already have all the proper we have all that is we are supposed to have, like all the proper information. So the last thing we have to solve for is number of moles. We're told that the gas is methane. So, and we're told the mass of the gas, mass of CH4 or methane is 4.50 grams. So Remember, the number of moles of any gas is mass divided by molar mass. So the number of moles of methane gas is going to be mass of methane gas, CH4, and then the molar mass of methane gas. So number of moles is going to be, mass is going to be 4.50 grams divided by the molar mass of molar mass of the CH4 gas is 16.04 gram per mole. So of course, input this information in the calculator, we end up with 0.28055 mole. So now we have all the information we need to substitute. So we have work done, let's not forget, equals negative R nRT ln V final divided by V initial. So we're just going to substitute into information. We have work done now equals negative 0.28055. So the number of mole times, we'll go back to see what R is 8.3145 joules per mole Kelvin. 8.3145 joules per mole Kelvin. Okay, times temperature, which is 310 Kelvin. So all of that information, ln V final divided by V initial. So that's going to be, V final is going to be 16.0 dm cubed divided by V initial, and that's going to be 12.7 dm cubed. So you cancel out all of the information, mole, Kelvin, of course, dm cubed. We're going to cancel out because the units just easily cancel. So now we have all of this information. We're going to do negative 0.28055 times 8.3145 times 310. We're going to get that information to be 723.116 joules. Okay, and times ln 16 divided by 12.7. So that would be 16 divided by 12.7. So when you have all of that information, remember the negative. So you have work done is going to actually be equal to negative 911.0123 joules. So yeah, but one thing you have to note is that the work is not actually done. You see that we're given our information in trig sig figs. We have 4.50, we have 12.7. When we add to find V final, we have 16.0. So everything we've been given actually has been in 3 sig figs. So we have to put our information and round up to whatever we have. We have to do the approximate value in 3 sig figs. So actually work done is actually going to be approximately negative 911 joules. So this is our answer. Work done is negative 911 joules. So this is how you answer this particular question. If you have any question, please put it in the comment section. Salam and welcome. So today we're going to be working on the question on the screen that says a sample consisting of 2.0 mole of helium is expanded isothermally. So exothermal expansion is what's going on here. So which means the V final is greater than V initial, meaning since an expansion, the final volume is greater than the initial volume. So this happens isothermally, which is constant temperature, or the change in temperature is 0 at 0 degrees. So what this is saying is that the entire process of expansion occurs at a fixed temperature of 0 degrees. So the volume goes from 5.0 dm cubed to 20.0 dm cubed. Calculate the work done by the system when the process occurs against constant external pressure equal to the final pressure. So the first thing you have to remember is that the formula for work, right, when you're dealing with a constant external pressure question is negative pressure, that is external, okay, times a change in volume. But this particular question has a twist, and the twist is that the external pressure is not given to us, but we are told that it's going to be equal to the final pressure. So what this is saying is that the external pressure is going to be equal to the final pressure. So we can rewrite the work done equation as W equals negative P final change in V. So change in volume. So that's basically what's going on here. Now, to consistently work on whatever this is, we have to first of all like write out the parameters, right? We're given n equals 2.00 mole. Okay. We're given the temperature to be 0 degrees Celsius. We can convert 0 degrees Celsius to Kelvin by just adding whatever this value for in Celsius is to 273. So we have 273.15 plus 0. So the temperature is really just 273.15. And then, of course, we add the Kelvin conversion. Then we write out the fact that the V initial is 5.0 dm cubed. The V final is 20.0 dm cubed. So basically, we're supposed to like solve for this. So the first thing you have to note is since we're going to use the final pressure, we can use the ideal gas equation like we've been doing anytime we have the perfect gas law. So ideal gas equation, we're going to have P V equals nRT. Well, since we're dealing with final pressure and the temperature is constant, the temperature is okay, number of moles is constant, the gas content is constant. The only thing that really changes from our question is that we have an initial volume and a final volume. And our question is telling us to look for the final pressure. So we have PF. Now we have two values for volume. I got the initial volume and the final volume. We're just going to put F here for final volume because we're dealing with the final part of the process, since that's basically what we're supposed to solve for, the final volume. So PV equals nRT. So that would just be the P final is the same thing as nRT divided by V final. So that's 2.00 mole, okay, times 8.3145, which is just simply kilopascal dm cubed, okay, per mole Kelvin. So this is the gas constant we're going to use. The unit is kilopascal dm cubed or kilopascal in liters per mole Kelvin. Of course, times the temperature, 273.15 Kelvin. All of that information divided by V final, which is just 20.0 dm cubed. So, of course, let's cancel out the information. So, cancel out mole, Kelvin, Kelvin, and then dm cubed, dm cubed. So dm cubed, dm cubed. So the P final ends up being, just putting all of this information in our calculator, we're going to end up with 227, okay, 0.111 kilopascal. So basically 227.111 times 10 to the power 3 pascals, but let's just keep it in kilopascal. So basically we found the final pressure. So we have the pressure that we're going to use. Now we're going to have to focus on going, like, don't forget what this question is, right? The formula is, just rewriting it for you, is negative P changing V. Well, we know it's P final. We've gotten what that is. Now we have to deal with change in volume. We know we go from 5.0 dm cubed to 20.0 dm cubed. So that's just saying change in volume equals 20 minus 5 is the same thing as 15.0 dm cubed. So yeah, that's basically how it works. Before we go on, I need to quickly explain something to you guys. You can see that pascals is the same thing as, Pascal is just basically a unit for pressure, but Pascal is also equivalent to Newton per meter squared. Don't forget that pressure really is force divided by area. So the unit for force is Newton, the unit for area is meter squared, hence Newton per meter squared. And that is what is equivalent to pascals, right? Because you can see here that we've got dm cubed and we've got pascals. We cannot solve when our parameters or our information is not in the proper units, because we're not going to be able to properly multiply and get the correct answer. So what you're going to do now is, we know what this is, right? We know this one right here. We also know this is dm cubed. We're going to go from dm cubed to meter cubed in order for us to work with this and for us to properly succeed. You're going to see the value of all of this at the end of the day. So now, dm cubed to meter cubed, we need the standard information, right? So 10 decimeter is the same thing as 1 meter. Hence, 10 decimeter all cubed is going to be equivalent to 1 meter all cubed. So doing the math, we'll see that 10 times 10 times 10 is just 1000. Dm times dm times dn is dm cubed. 1 times 1 is 1. Meter times meter times meter is meter cubed. So what this is telling me is that for every 1 meter cubed, we've got 1,000 decimeter cubed. Well, we've seen that the change in V here, right? Change in V is 15.0 dm cubed. And that's what we're trying to go from that to meter cubed. So we can just use dimensional analysis and write 15.0 dm cubed. Okay, so we're trying to go from 15.0 dm cubed to whatever it is in meter cubed times 1,000 is at the bottom, dm cubed, and then 1 meter cubed up top. So we cancel the dm cubed, we cancel the dm cubed. And what we end up with is 15 divided by 1,000, which is the same thing as saying 1, 2, 3. So that would be 0.015 meter cubed. So now this is what we're going to use when we're solving our question. So going back, we see that work done is equals to negative P external or P final, okay, change in V. So that would be work done equals negative, what's P final? Would it be 227.11 times 10 to the power 3? 227.111 times 10 to the power 3. Okay, pascals is the same thing as Newton per meter squared. So that would be Newton per meter squared times change in volume, which is simply 0.015 meter cubed. That would be 0.015 meter cubed. Of course, we can cancel this out. So that would be meter squared cubed, remove that. So that would be negative 227.11 times 10 to the power 3 times 0.015 is going to equal negative 3406.66 and then Newton meter. So that would be Newton meter. Please note that Newton meter is the same thing as joules. Okay, because what is really the formula, the fundamental formula for work is just force times distance. So force units is Newton, distance units is meters. So Newton meter is the same thing as joules. So now we go back to the top of the question, right? We see that our question, the smallest sig figs that we're given is 2 sig figs, which is here, right? 5.0 dm cubed. So we have to put this answer, the approximate value, in 2 sig figs. So that would be W work done equals negative 3.4, okay, times 10 raised to the power of 3 using scientific notation, Newton meter, or work done equals negative 3.4 times 10 raised to the power of 3 joules. So this is basically the answer to the question. If you're wondering why the negative is in front of this particular work, is because the work is done by the system. So the expansion process is being done by the system. Hence, what is going to happen is that it's going to be losing energy. So for example, the energy that you have before you maybe clean your room or before you do a task is going to be more than the energy after you do a task. So this negative is showing us that there was energy lost by the system because they did the expansion process, and the value of the energy loss is 3.4 times 10 to the power 3. That's why we have to denote it with negative to show energy loss. If it's energy gain, it's going to be positive. But in this case, the work is done by the system in the expansion process. Hence, we have energy loss, which is why it's denoted in negative, or which is why we have a negative value. I wanted to mention that I'm a personal tutor that helps students succeed and get A's in all their STEM related courses. So if you need any help, make sure you email me at shuhabitutoring@gmail.com. I teach high school, middle school, and college level students, as well as I do private and personal tutoring in STEM related courses. So make sure you email me if you have any questions or need any help or want to book a session. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.